don't know how to say it.
It's Jader.
Jader, okay,
Yeah.
so go ahead. Oh, yeah.
Okay, so my name is Jader. I am a postdoc working at the Hebrew University with Professor Anus Din. Today I'm going to be talking about spline error mitigation for dynamical circuits, okay? So as we know, dynamical circuits are quantum circuits that incorporate some classical processing. And this is usually done by using mid-circuit measurements and feed-forward, okay? So I put a small circuit over there. And this is useful because dynamical circuits can overcome some limitation of the current hardware that we have, because we can make the circuits shallow by substituting, using less 2-qubit gates at the cost of using more measurements and extra qubits. Some of the applications that we have, for instance, it was done quantum Fourier transform using dynamical circuits, prepare highly entangled quantum states like the G8Z state using dynamical circuits, gate teleportation. Also, it was shown to overcome baryon plateaus for parameterized quantum circuits. So there are many applications, and of course, quantum error correction as well is a type of dynamical circuits, because we are doing measurements, and depending on the result, we have to do this feed forward, which will be the correction. So this is also a dynamical circuit. And as I said before, because we are adding these extra measurements, that's the price that you're going to pay. And the measurement, of course, they are not perfect, so they will contain errors. And for the dynamical circuits, this is important, because if the measurement has an error, this error will propagate through the circuit, so there is this extra problem. And depending on the platforms, the readout error can be very important, like for superconducting circuits, for instance. And what we can do about it is quantum error mitigation. So for readout errors, what we have to do is first propose an error model and implement some calibration measurements. So this is usually the type of model that people use, which is a classical model. So we have the true probability distribution, the observed probability distribution, and they are connected by this M matrix, which is called sometimes error matrix or calibration matrix or assignment matrix. And if we can estimate this M matrix, we can do this operation in post-processing and recover the probability distribution. The problem is that most of the time is difficult to obtain this M matrix, because it's a complicated matrix. Because usually the errors will be correlated. So it is actually not scalable to obtain this M matrix. Of course, there will be techniques that we can use in order to make this problem simpler. For instance, there is this M3 idea that we can reduce the dimension of the M matrix. Or, as was discussed previously before, we can also do this bit flip averaging, which is a type of randomized compiling for measurements, where we can simplify drastically this M matrix. And then the problem becomes scalable. But even if we implement this type of techniques, we have to rely in updated version of this M matrix, which can be kind of difficult, because imagine if you have your dynamical circuits, your dynamical circuit, and you have to implement this correction in real time, and probably you have to do some type of resampling, and you have to trust that this M matrix that you have is calibrated. So it would be nice to have some type of technique that doesn't rely on a updated, calibrated matrix. And what we can do, usually what's done in error mitigation is this idea of amplification of the noise and error extrapolation. And this type of technique, it's useful because then we don't need to rely on an updated model for the error. And the idea here would be nice if we could do something similar for the readout error. So imagine, for instance, let's describe our M matrix in this symmetrical way, which is very simple. And suppose that we could somehow amplify this error by doing some type of measurement in which effectively the M matrix, we could amplify it, like the effect, like cube or to the 5, for instance. If we could somehow do this type of measurement, we could combine these results in post-processing and then effectively mitigate the error. So epsilon here is the error parameter. If epsilon is 0, we'll have the identity. And so as you can see here, In the regular case, m will be proportional to epsilon, so it will be linear in epsilon. But if we combine these results in post-processing, then we can mitigate the effect of the error, okay? So the problem is, okay, how can we actually implement this type of measurement? And that's what we are proposing here, which is this parity-based noise amplification. So the idea is that we want to implement this type of amplification of this measurement by using parity. So for instance, in this case, if we want to obtain this cube, this factor of 3 amplification for the measurement, we are going to implement 3 measurements and then consider the parity of these results. So for instance, if we have the 1, 0, and 1, we do this addition model 2 here and obtain 0. That will be the effective result of this measurement, of this scheme. So if we have only 1 measurement, the parity will be the result itself. If we have 3 measurements, then that will be the results here. Okay, these will be the results. So that's how it works. But why this is useful? So the idea here is that this is useful because, for instance, consider again that the M matrix is symmetric. The effective result here that we are going to obtain actually is the same as M cube. So parity gives, in this case, when the M matrix is symmetric, parity is giving the same result as M cube. So you can do the math and you can see that that's true. So this is great because then we can use this method to calculate the parity and mitigate the readout error. I know that I am showing this result here for this particular case, which is symmetric, but the point is that even when this matrix is not symmetric, this final result is still valid. So this is nice because we can mitigate the readout error. Okay, now that we understand this idea, probably you might be thinking, okay, if we can do these 3, 5 measurements, like it's not more practical just to take the majority vote, like sounds more reasonable, like just take the majority vote and that's it. But the problem is that actually, if you have this idea, this is actually a good idea, and majority vote gives the same result as parity. If you do the math, you will find out that majority vote gives exactly the same result as the parity. But the problem is that when you go to the real device, you have to take into account the decay. This is actually an experimental result that we did using the FACE device in IBM. And here we are measuring, doing 10 measurements in 20 qubits, and we are seeing how the population of the excited state is decaying. So if you take into account the decay, we will see that decay is actually very bad for the majority vote. Like it will degrade this result. And over here, now I am going to show you some simulations where I'm comparing the effect of parity and majority vote. So I'm preparing the state in the 1 qubit in the excited state and considering a measurement with readout error and considering the decay. And I comparing parity and majority vote. And in each one of these panels I changed this ratio here between T1 and delta T. Delta T is the time of the measurement. So as you can see, if T1 is very long, then of course majority vote it will work because the qubits will not decay, and parity majority vote works. They work equally. But when we go to more realistic scenarios, then we can see that actually majority vote doesn't work, but the parity keeps working. So in these plots here, there are 2 main results, 2 main ideas that I want to point out. First, oops. Okay, so the first idea is that majority vote doesn't work. And the second idea is that, as you can see here, parity is actually not converging like exactly to 1, what should be. And that's happening because, of course, the decay is also affecting the parity. And we realized that, we realized that we could fix this by considering some dummy measurements. So dummy measurements are some extra measurements that we are going to implement. We are not going to use these results. The only point of using these dummy measurements are to correctly amplify the effect of the decay in such a way that we could eliminate the decay, the first order in the decay, and actually the term that will remain will be proportional to gamma times epsilon, where epsilon is the readout error. And when we implemented these dummy measurements, then the result converges to the ideal, to the value that it should be. So the idea is that parity works correctly with these dummy measurements. Okay, so now that we understand how to implement these ideas, I want to show like a example of how can actually implement this in a circuit. So this circuit here is to implement this CNOT between qubits 1 and 5 using a dynamical circuit. So this will be the zero order for the parity. Okay, if we want to implement the first order, we have to combine this result in post-processing with this next circuit, with the result coming from this next circuit here. So over here, I'm doing this amplification of factor 3, where I'm using 3 measurements plus the dummy measurement that I talk about. So if we combine these results, then now I'm going to show here the fidelity of the ideal target result against the result to be obtained by the parity. So as you can see, if we go to higher orders, we can approach the fidelity 1. So that's how we can implement this in practice. Okay, what else? Also, I want to comment that this also works in the case where the measurement, the M matrix, contain correlations. So over here, I'm doing the simulation as well, where I can control the level of correlation by this factor lambda. And as you can see here, and I'm comparing 2 results. Okay, so first I'm plotting here the norm of the target probability distribution minus the probability distribution obtained by using parity and obtained by using a local filter. So in the case where I don't have correlations, so lambda is equal to 0, if I apply the local filter, this norm here will be 0 because it works perfectly. And as you can see, the parity also works, but I have to go to first and second order. But when I start to increase the correlation, then of course, for instance, take this case where lambda is equal to 1. So then the local filter doesn't work anymore. But the parity, is indifferent of the presence of correlations. So this is nice about the parity. And now I'm going to present an experimental result where we are implementing this circuit here to generate the G8Z state. Okay, actually, we are implementing only this first part here because the second part here we can implement in post-processing. So when we did this experiment, that was the result. So as you can see here, the result is actually not that great. Like the different colors here are the different orders of the method. So the green bars should be like the best result. And this bar here, the last one, is a G8Z state, right? So this should be 0.5 and the other ones should be 0. But as you can see, like that's not as good as we hoped. And we start to realize doing other experiments that there was problems in the initial state preparation. And we also realized that we could use the same idea, this mitigation technique, to mitigate the errors in the initial state preparation. And the idea is basically the same. Like you implement now, before you start the circuit, we implement this conditional X. So, of course, if there is no error, then you get the ideal initial state, which will be the ground state. But if there is some error here, of course, there will be an error associated with this measurement. And again, we can amplify this error, recombine the results in post-processing, and then get a better mitigated initial state. So when we perform this experiment again, but using this strategy to mitigate error in the initial state preparation, then the result is much better. And we can see here that we are tending to the correct result. Like if we compare with the other previous results, we can see that the next one is much better. So just to summarize, I want to say that now we have in our group this collection of techniques to do error mitigation, where we can mitigate error in the initial state preparation, in the readouts and the final readout measurements, and in the circuit itself by using the SKIC and PES-CT techniques. What I think it is, these techniques can be used, of course, for dynamical circuits, which is also very cool. And what I think it is very important here to point out is these techniques, we don't rely on a previous characterization, and they are also resilient to drift on the error. So yeah, that's it.